Hi, I'm Noah, and I'm the mechanical engineer for our senior design project. Our project is working on a bedside table with an XY rail system that automatically aligns a charging coil with a phone when it's placed on the surface. So at the start of the semester, my focus was researching the best way to implement this kind of system. I looked into a few different types of linear rails, starting with gear worms, which are known for their precision and durability. I also looked at systems used in printers, such as this one here, and CNC machines. And I ended up going with this design because they're practical, reliable, and they're commonly used in a lot of different things. So there's a lot of research to look at for those types of systems. Um, so next, I started to sketch up some design ideas. The first idea was this round table here with a ridged gear along the edge. A motor would rotate the table while another motor moved the coil across the surface. Uh, this approach was creative, but we eventually decided not to do the round uh, table. I started to sketch up this square table design instead, and we looked into similar systems, and we found out that this one was pretty practical. We went with this gear worm here, and then we thought maybe we could mount the other one right on top of it so we get that full tabletop coverage. Um, and then for the final design, we ended up going with this, like similar to the printer designs, where you have two parallel um, rails, and this one in particular is controlled with a belt so that these ones are in sync, these two. And then that controls this horizontal rail with its own motor attached for this left and right movement. So after finalizing the shape of the table, we started to test out some of the parts in the XY system. We first started testing out this single rail to see how well we could convert the rotational motion into linear motion. The test worked. It was proof of concept, and it showed us how the system would perform in real world conditions. It also gave us a chance to identify areas for improvement, such as improving the gear ratios for speed and things like that. Yeah, so that pretty much wraps up the mechanical progress that we made this semester. Obviously, there's a lot more to be done, but I think that this is a pretty good start.
Hi, my name is Lucas Douglas. I'm part of Group 8 for the wireless inductive charger. I have been in charge of prototype development for the semester, and I'm here to show what we've got so far. For our design, we obviously needed a sturdy enclosure. It's a pine box, just made with simple boards you find in a hardware store. As you can see, it's hinged just so that way we can get to the inside for quick prototyping. It is a glass for the fact that we can have our inductive charger pass its charge through it. Originally, we had talked about using plexiglass. Glass has ended up being cheaper, and we sized the box and the design according to what the most cost effective option was. Looking at the actual design, we can see that the XY motor is fully assembled for moving the charge coil per Noah's design. If I hook it up, I have it on a simple oscillation for the two stepper motors. We have it working fairly slow right now since it's operating solely off USB power, but as the video runs, you're going to see it move pretty slowly. The point of this design was to have extremely high precision. Part of that means we ended up sacrificing a bit of speed. We can correct that if we're willing to up our stepper motors. I'm going to kill this before it moves too far. We can correct for some of the sluggishness by upping the stepper motor. This one is pretty low power rated, and when we attempted changing the gear ratio for the spiral gear, we ended up not being able to turn it just because these small stepper motors don't output enough torque. In the spring semester, what we hope to do is add a additional rail along both the top and side of the box. This will allow us to have an infrared laser sensor that will slide across. For that, we do not need to have the same level of precision that we have for the XY coil position system, since for that, our IR sensor is going to get us a general ballpark for where the phone is, while we'll have the Hall sensor to give us really precise readings. The goal for the spring semester is we're going to mount the Hall sensor near the coil. This is the wireless coil that the phone connects to. Power cable is routed here. Once we have the Hall sensor, we'll be able to use the IR sensor to move this to a general region close to where the phone is, and then we'll then be within a short enough range that the Hall sensor is going to be able to get us to our exact target. Some challenges we had with this design. We had a bit of trouble with the rise on the chain for this. The chain is to ensure that both, for the sake of convention, we'll call this the Y direction. To make sure that motion in the Y direction was uniform, we have both axles for Y direction movement chained together so they can be driven by this single motor. Challenge we had was that we couldn't find a chain length that was perfect for the distance we have between our two axles. So what we have here, if I remove the design from the enclosure, you can see we actually have a tension bar in place to make sure that the chain has constant tension and motion is evenly translated between both of the Y direction axles. We currently have it hooked up and running off the Arduino microcontroller, courtesy of Steven. Just the two stepper motors hooked up at this point. We don't have the feedback hooked up yet. That's our goal for the spring. As we can see, the first version of the prototype is fully assembled and functional. Because we are running entirely off of 5-volt power, both for the charge coil and for our microcontroller, we can just use a commercial wall adapter to power the entirety of this design, converting AC wall power into DC power for both the motors and the charge coil. Julia is going to talk more about the sensing feedback that we're going to use to make sure this design accurately places the charge coil under the phone. So I'm going to pass it off to her.
Hi, so I'm going to quickly jump into my portion of the project that I've been working on this semester and will be finishing next semester in Senior Design 2, which would be the tracking and sensing portion of this project, which would be tracking and sensing the location and coordinates of the cell phone on the table, and more precisely the location of the coil to get that proper alignment. So before I hop into the design, I want to go through some of the iterations that we've been through as a team, just with different ideas that we've floated and tested. The first thing I want to talk about is the resistive touchscreen, which turned out to be far too expensive with very difficult interfacing, difficult to write algorithms, and still less precise than the option we ended up going with. Hall sensing only would be great if the table was very, very small, but in order for the project to still be used as an actual table, we need something with a little more range. So that's where we thought of the IR tracking, which is precise for sensing the location of the cell phone, but not the actual coil, which we need for the coil alignment from the transmitter. So what we ended up going with was a combination of both, which I'll get into right now. So a little overview of the design. I've made a graphic here. So this is actually not the same linear rail system that's been previously talked about. This one will be sitting on top of the table, and that dotted line background would be representing the surface of the table. We have two independent rails placed in an L shape, controlled independently, with two cards both having lasers on each of them, and then there would be a receiver at the end of each of those red dotted lines, which represent the beam of light. And then I have some coordinates labeled on the cell phone for where that beam of light would be interrupted. So just another view here that would show how the beam of light would be interrupted around this area is where we would have the receivers positioned wherever the other ends of the table without the rails were located. So a little overview on part selection. This is just a little bit about the laser we chose, which would be the KY008 laser transmitter module. And on the screen, I've just got some of the specs. And what's important is the little Arduino interface. So chosen for easy interfacing with the Arduino microcontroller. Compact size and low cost for prototyping is very important. We're definitely going to go with a higher precision, better quality laser for our final design. And a similar thing for the receiver. I also have some specs up on the screen with the PCB size, supply voltage, and I think my little bubble is covering this up, but what is behind my head right now is the circuit setup with the laser that we just looked at, but right here is going to be the receiver. All right, so the last thing I want to go over is the testing procedure that's planned for this whole setup. Now that we have the rails working, this should be in the works very, very soon. So the first phase of the testing would be the setup and calibration. Like it says right over here, run the system without any objects to make sure there's no beam interruptions, kind of like noise but for light, and see the response to ambient IR noise levels to determine if additional shielding or filters would be required. I'd say for this phase, it's okay for a little bit of ambient noise or to do a lot of this testing in a darker environment because, like I said, we will be upgrading the lasers. And the last phase of this would be to pass an object through the IR beam at known position and just record those timestamps for beam interruption and restoration. And the last bit I have here, just use the known distances to measure how quickly the IR sensor is responding to beam interruption and restoration. This will be really helpful when it comes time to write the algorithm for this. Phase 2 of the laser testing would be the object detection test, which has 2 phases in and of itself. We're going to start with our static position test, placing the phone at multiple positions. It says along the rail, along the table, and record the time intervals for each position. And then, of course, compare recorded intervals to expected values based on the calibration data. And for the dynamic position test, we're basically going to be moving a test object along the rail at a controlled speed, whether that be using a motor or just the best we can do by moving it ourselves. Log the timestamps for when the beam is interrupted and restored using data from the receivers, and calculate those positions, verify actual positions, and that's really going to lay the groundwork for the coding portion of this project, which I'll get into a little later. And to continue on with the testing procedure, we're in phase 3 now, which is testing the conversion accuracy, which would be using the measured interruption and restoration times to actually convert that into XY coordinates that can be not transmitted, but to be transferred to the lower rails for coil positioning. Compare those calculated coordinates to physical measurements. And for a little bit of error analysis, we would be logging any discrepancies between the calculated and actual positions and adjust conversion formulas for calibration as needed. And for phase 4, finally, is the motor and sensor synchronization. So ensuring those IR sensor readings do not interfere with the motor control signals, as well as verifying that the beam interruptions trigger accurate motor responses for positioning. Real-time tracking is kind of a future consideration. We'll see if we have time for it, but to simulate the phone being placed at different positions on the table. And this is what I was talking about earlier, a little pseudocode flowchart to kind of get an idea of the algorithmic portion of the IR sensing. So I'm not going to go over this completely, but we can take a look at all the elements. What I really want to touch on is the main function. So we have the setup function. The homing sequence is extremely important for coordinate accuracy, and the main loop is really what I want to get into. So the receiver is constantly being monitored. Is the beam interrupted? We would record the time, convert to coordinates based on all that testing that I just touched on, log position, and send motor commands with some error handling in between. And I'm going to pass this off to Stephen.
All right, thank you, Julia. My name is Stephen. I'm a computer engineer, and I'm going to be working on the sensing with Julia, as well as the motor movements with NOAA and basically tying everything together with the Arduino microcontroller. For this Hall sensor, you can see here we have a conductive plate with constant current flow, and it's subject to a magnetic field, which is the magnet in this case in this diagram. And when it's subject to the magnetic field, this parallel plate disperses the positive charges as well as the electrons to opposite sides of the plate, and depending on the distance, it'll basically determine how strong the magnetic field is, which will help us locate the receiver coil of the phone. And that's basically shown here. Julia talked about the IR sensing to just generate the general location of the phone and using the XY coordinates, and then the Hall sensor will basically locate the RX coil, which is shown here. The RX coil is going to receive the power transfer from the transmitter coil that we have on the cart that will be underneath it. So that's shown here. The Hall sensor will be locating that coil, and the transmitter coil will then be able to power the transfer effectively. So just general interfacing for the Hall sensor, just some steps to go into it in the future. Basically, we want to make sure that the Hall sensor is on the transmitter coils cart and not the receiver coils, obviously, because we want to be able to move that coil to the phone. We want it close as possible to the surface, because without it being close to the surface, we'll get really bad readings, maybe not even a reading at all because of the distance. They're very sensitive and deal with very small proportions, so we need to make sure it's as close as possible. Also, aligning the sensor is important, because if we aren't aligning with the magnetic field lines properly, we won't get proper outputs as well. And it'll be connected to the analog pin of the Arduino. And before any testing or calibration or anything can be done, essentially we want to establish the baseline field strength within the table and different values over different positions without any phone present, so that I'll be able to reduce any noise and improve our accuracy. To test and calibrate everything, essentially, we want to turn off the transmitter coil because we don't want any interference from the transmitter coil, because we're trying to locate the receiver coil. And the basic routine for the idea right now is when we place the phone with the key inductive charging coil, it'll be positions that are relatives to the sensor, and we're going to measure the raw output values of the Hall sensor, and we're going to basically determine the maximal strength that we have for the magnetic field. And by mapping the output values of the Hall sensor throughout the whole table, we can basically ensure we know where the location is of the phone for future experiments. So going into the measurement phase, we're going to apply a low-pass filter that'll reduce any noise and account for any environmental interferences. This way we can get the accurate readings that we want. And so we're going to establish what we want for magnetic field readings, essentially. So what we're going to do is have the transmitter coil that will move incrementally along the x-axis. It will record any Hall sensor outputs, and it will plot them so that this way we can have this like XY coordinate system. It'll be the same system for the y-axis, and we will determine the thresholds, which will be the difference between the baseline values without the phone that we recorded, and then all the values of the x and y increments, and then we could determine the highest value from there, and that'll be the location of our receiver coil. And when we initialize the system, we want to have the transmitter coil at a starting position, which will be the corner of the table at the 0, 0 coordinates in the corner of the table. And after it's initialized, it'll go through the search phase, which is basically the same thing as determining the field strength. We'll have the x-axis, y-axis, move along those, and we'll determine at different steps what the highest reading is. And once both the x and y-axis are covered, it'll move to the location with the highest magnetic field strength. And this will basically refine our laser sensing and give us the best power transfer that is possible for this project. And this is just a general code flow for the project. This semester was mostly the prototyping, that Luke worked on and Noah worked on, the motors, and we were working on the sensors, but we didn't really get to put the sensors on the unit yet and get to test anything. So this is just general code that we have, a general flow that we could have. So we basically will just initialize a system, and we want to make sure we turn off the transmitter coil because we don't want any interference from it. Since we are locating the receiver one, you don't want two coils running at once. To begin the search, we'll have small steps moving along the x-axis. Same thing will be for the y-axis. We will read in the sensor values, and once that max magnetic field position is located, simply we'll just move the coil there. We'll make sure we have fine adjustment algorithm there to make sure we're actually aligned and not just having some misreading happening. And then once the coil is turned on, it'll transmit the power to the phone, and we're going to have a basically real-time operating system that'll recheck the strength to ensure that we're still getting the charging necessary, and then we will adjust the position if the phone moves and handle any errors and reinitiate the search if necessary. And this is just generally how it will be working for our project, and next semester we'll definitely be more focused on the code as well as the embedded side of this project. Thank you.